Hey everybody, it's Mr. Oliver. Today I want to run through a quick little review of Unit 1 on fluids for AP Physics 2. If you have the outline that I gave you, go ahead and get that out. Maybe get something to write with and some scratch paper as well. So let's go ahead and get to this and let's get started. All right, Unit 1 on fluids. We're going to start off, but just by kind of talking a little bit about basic fluid systems. So, when we're talking about a fluid property, we're talking about how fluids can take the shape of their container. They're also non-solid, and also we're talking about liquids and gases. So don't forget about that. Now, some of the fluid properties that we see typically are things like mass, density, viscosity, specific heat. Remember C sub P. Things like that. Those are kind of fluid properties we're talking about. Now, when we measure these things, the fluid properties really are specific to only three things that we care about, at least at the beginning. So, what we want to do first of all is remember that mass is a measurement of how much inertia or how much matter there is, and we got to use kilograms for that. Now, volume. There's a lot of different units for volume, but we got to make sure we're using cubic meters for that. So let's see if I can do a cubic meter. So this thing should be superscripts. All right, so that's a cubic meter. And then, of course, density is our last one. And density is a fluid property that kind of encompasses a bunch of factors. And the reason why we use density is because it's usually a known quantity. So, for instance, the density of water is 1,000 kilograms per cubic meter. So, when we're talking about density, we're always measuring things in kilograms per cubic meter. All right. Now, of course, the definition of density is always the mass divided by the volume. So, what's nice about this is because if we know that the density value is a known quantity, that's a constant, then one of these two terms, if we know one of these two terms, we know the other. And usually what we'll do is we'll rearrange this relationship and put it in terms of mass. So therefore mass is equal to the density times the volume. And that's a lot easier. Ooh, watch my spelling there. That's a lot better relationship. Now, if you remember the symbol for density, it's not a typical American letter. It's a Greek letter. So we're talking about density. We're talking about the Greek letter rho. Volume is typically a capital V, and of course, mass is usually a lowercase m. And guys, please forgive me for my terrible mouse writing here. It's pretty awful. Now, if you remember in class, we did a little demonstration where we had a little flask of uh, some kind of a little graduated cylinder, and we filled it up with a bunch of different fluids. And typically, what happens is the denser the fluid, the lower down in this column it goes. So maybe we filled it up with let's say we filled it up with water at first. And so this would be all water. And then maybe we fill it up with oil. Well, oil is a less dense fluid than water, so the oil would float on top of the water. And that's just a pretty typical demonstration of how density does matter. And as long as we know those densities, we can figure out how the two things float relative to each other. Sorry, guys, I gotta kill this music. Now, we're talking about hydrostatic pressure, what we're doing is we're talking about how uh, if I have a container and it's filled with some kind of a fluid, then that container will always have pressure depending on the molecules that are inside the container. So if I have some little molecules of, let's say, a gas, then the gas molecules, as they're moving, those gas molecules will actually hit the side of the container and reflect off. Because the way we do this is we treat these molecules as though they have kinetic energy and momentum. And so anytime that molecule hits the side, it's going to exert a force on the side of the container. And what we can do is aggregate all those forces of all the molecules bouncing around, hitting the container, and exerting a pressure. So if you remember, pressure is just a relationship that describes how that force is exerted over a surface area. So pressure is equal to the force divided by the area. And so that way is if we know what the pressure inside of the container is, and we know how big the container is, we could know the pressure value and the area value. And so we could rearrange this in terms of force. So the force would equal the pressure times the area. Now, in cases of a fluid where it's a liquid form, pressure actually depends not only on the molecules moving in the container that it's hitting on, but it also depends on how tall that water column or that fluid column is. So, for instance, if I have uh, a container like that graduated cylinder earlier, and I fill it with some water, then whatever that column height is will actually determine different color. Whatever that column height is will actually determine how much pressure you have at different depths. So up here at the top, the only stuff above the surface of the water would be the air. And so up here at the top, we would call this like pressure number 1. And so that pressure would be the atmospheric pressure. ATM. And down here at the bottom, well, this would be known as pressure number 2, P2. And it would tell you the pressure of not only the fluid, but also whatever pressure you have above the fluid. So if we call this water column having a height of H, then that pressure 2 would be pressure 1 plus the pressure due to all the water. Well, if you remember in your notes in our discussion, we said that that pressure due to the depth is equal to the density, rho, times G times H. And so whatever height that is, that's how much, what factor you multiply your density times your G value for gravity, and you can figure out the pressure due to the depth there. Now, there is a term that we really didn't talk about much, and that's called absolute pressure or gauge pressure. Now, if I have a device that's actually a pressure gauge, let me see if I can pull up a picture of that real quick. Here's a pressure gauge. All right. Typically, these pressure gauges are arranged in such a way that a zero pressure would correspond to the atmospheric pressure, because you don't want to read a gauge and say, hey, I've got to also consider absolute pressure. So what they do is typically they say gauge pressure, which is what you would read off of this, is the real pressure of whatever fluid or system you're trying to measure minus the pressure of the atmosphere. So gauge pressure the way I would describe what a gauge pressure is, I would say that's just the actual total pressure minus the pressure of the atmosphere. Sometimes you would call this total pressure the absolute pressure. So just realize that that's what we're talking about. Is typically the gauge pressure is just whatever effects you have minus atmosphere. So in terms of our little equation that we wrote, if I were measuring the pressure at the bottom of a swimming pool, for instance, with a gauge, that gauge pressure would be only the pressure at the bottom, oops, of the pool. So that would just be the rho GH term. So P2 minus P1 in that sense, if you're measuring the pressure at the bottom of a pool with something like this, would be rho GH, or the difference between the pressure at the top of the pool, which is P1, and the pressure at the bottom of the pool. And so that would be the gauge pressure of the pool at the bottom. Now, one other thing that we talked about is something called Pascal's principle. And Pascal's principle just says that the fluid, as long as it's a liquid, can't compress. And so whenever you have fluids that can't compress, that means that if I have a tube of some sort, then if I change the pressure at one end, let's say it's a water hose, so I turn on the one end of the water hose, whatever pressure happens at this end, because I turn the valve on, as long as there's fluid filled up in this entire hose or pipe or whatever, if I add 10 pounds of pressure at one end, then at the very other end, I would also have 10 pounds of pressure. And so the pressure value is theoretically transmitted from one end to the other equally. And where you see this is whenever we have things like hydraulic jacks. There's a real simple little demonstration that we showed. Let's see if I can find that picture. Yeah, here we go. So something like this is what I would be talking about. Like if I apply a force at one end of this and this fluid is completely filled, all the pressure inside of this fluid is constant. And so when you end up getting a change in force on one end, that force can be magnified because you have a bigger area on the other end. And so what you end up with is a real simple relationship that says that the pressure at both ends is the same, but the forces will be different. And so you have this little relationship, F2 or F1 over A1 is equal to F2 over A2. Now, in the College Board's course guide, they talk about drawing free body diagrams and net force equations from on fluids, and that's okay. You can do that because let's say that I've got a container of some kind of a fluid. So let's say I just come over here and it's a beaker or something like that. I fill this guy up with fluid. You say, well, how do I draw a free body diagram on that? Well, what you do is you'd say, well, at any one point, you can just kind of take out a chunk of the water. And so like if I just came over here and I said, hey, here's this chunk of water, even though it has some physical size, you just still treat this as any normal object. And so you'd say, hey, that chunk of water has forces acting on it, such as, like maybe there's a force of gravity pulling down. That's pretty small. Maybe there's a force of gravity pulling down on it. And maybe there's also some, maybe there's a buoyant force or something lifting up on it. And so as long as you draw the force arrows just like you would for any other free body diagram, it's pretty simple to talk about drawing free body diagrams on water. So as long as you keep it as like a little chunk of the fluid. And where this comes in is whenever we're talking about the buoyant force. Buoyant force just means that objects that are immersed in some kind of a fluid typically have some kind of a force acting on it called a buoyant force. And what happens is, let's say, for instance, I've got a swimming pool, and you've got a a raft or some kind of uh, some kind of a little pool floaty or something like that. Then that object has got some kind of a force that lifts up on it. And the reason why there's a force that lifts up, this buoyant force, is because the density of this raft is less than the density of the fluid that it's sitting in. And that buoyant force is given by what's called Archimedes' principle. And so what we say is that the buoyant force is always going to be a real simple relationship that says it's equal to the density of the fluid times G times the volume of the fluid displaced. Ooh. And so if you remember, you can go back and look at your notes on that, that this buoyant force, that should be a subscript. Oops. As long as we know what the density of the fluid is, of course, how strong gravity is, and the volume of the fluid that's displaced, we can calculate exactly what that buoyant force is. Now, in your notes, we went through and talked about how you can describe what happens with objects that are floating. And if I have a floating object, the main thing that you want to know is that the buoyant force will be equal to the force of gravity. That's the criteria that means that says that we're going to have something that floats. Otherwise, it would just sink to the bottom. If this wasn't true, you'd have something that goes all the way down. If you had a buoyant force that was greater than the force of gravity, it would just float up. So this would be in a situation like if this was buoyant force was greater than the force of gravity, you would have something like a helium balloon that just kind of keeps lifting forever until that buoyant force changes because the density of the fluid changes. Now, after we got through all the static stuff, we got into talking about fluids that were moving. And we had a brief little discussion about laminar flow versus turbulent flow. It's not a really critical thing, but just know that when we're talking about laminar flow, really what we need to understand is that in laminar flow, we consider that fluid friction is negligible. So we just don't even really care about that. Whereas in turbulent flow, you do have to consider things like frictional effects and the way fluids may be moving and running into the containers that they're moving through. So like maybe you've got water flowing through a pipe or a tube or something like that. Then you got to worry about it. But typically in laminar flow, we don't consider the frictional effects. And so really what that means is that energy will be conserved. That's the idea of using a laminar flow model. And one big kind of key point of that is this thing called continuity. And the idea of continuity says that if I have any kind of a pipe or a river or anything that has some kind of a fluid running through it, that if I change the size of the tube, that what has to happen is the fluid has to compensate for that fact. And so the idea is that if you have a narrow channel right here and you've got some fluid moving through it, then right here at the narrow part of the tube, that speed is going to be really fast. And so in order to maintain continuity just means that the mass has to be conserved. That's really what they're talking about, is that however much mass you have coming in at this end has to be the same amount of mass that's going out on the other end. And so what will happen is if I'm moving fast on one end to maintain continuity, the speed will decrease on the other end. And so on this side, it's just going to be moving slow because the area is bigger. And you've seen that before if you looked at a river that's really wide, like the Mississippi River. It's really kind of slow. But if that river kind of necks down and gets into a really smaller width of the river, the speed will actually increase. And so it works both ways. You can go from fast to slow or slow to fast. And the mathematical relationship was pretty simple. It was V1 A1 is equal to V2 A2, where V1 would be the velocity at the beginning side. A1 would be the area of the beginning side. So when we're talking about area, we're talking about cross-sectional area. So if this was like a circular tube, it would be the area of a circle. And on the right-hand side, you got V2 A2. That would just be the velocity and the area at the other end. And then lastly, the last thing that we talked about in the unit was Bernoulli's equation. And Bernoulli's equation is essentially a conservation of energy formula, specifically for moving fluids that are moving. And this kind of relationship, you don't see a lot of calculations on the AP exam, but you will see information that has to do with the energy conservation side. So it's more of a conceptual question. But I would go back through and look at the couple of examples that we did in the notes and see how you actually use a conservation of energy idea. All right, and so that's all. That's the whole unit. And what I want to do is I want to leave you with a brief little practice problem. This is off of a released AP exam. And so in this problem, what's being said is that there's an experiment where some kids are doing this experiment where they got a force probe that measures the force pulling on this little hook, and they've got some kind of a block. And what they're going to do is they're going to put that block into the fluid, and you see how the fluid level changes when they put the block in. And so what's happening here is that they're showing that there's a difference in the force readings whenever they have it out of the water versus whenever they put it into the water. And so this is the problem statement. It says 2 groups of students are given samples of the same unknown liquid and are asked to identify the liquid. The first group decides to do this by determining its density, rho L. The students pour a volume of liquid into the graduated cylinder, then hang the long solid block of mass M from a force probe and lower the block partially into the liquid as shown above. So this is kind of what they're doing here. The students record the reading on the force probe and the volume reading V final on the graduated cylinder for various amounts of the block. And so the idea is that they're lowering this thing step by step into the water and recording the force at different volume levels. And so the first question says, on the square below, which represents the block, draw and label the forces that are exerted on the block when it is stationary and partially submerged in the liquid. Each force must be represented by a distinct arrow starting on and pointing away from the square. So take you some time, draw that out. And then the second part of the problem says derive an equation for the force probe in terms of the variables that you're given. So all these variables, rho L, MB, V initial, V final, and physical constants. Physical constants should just mean like G for gravity. Those terms must be in your answer. It's not a case where you can omit one or two. You have to put all these terms into the answer. So take you some time, work through that, and the next video I post will be a solution to this. Hey guys, I hope I did okay. It's kind of weird doing this via the kind of setup that I've got, doing it online, but I hope you got something out of it, and I'll see you next time. Thank you.